perhatikan. Nanti kalau terlalu cepat atau nggak jelas, silahkan bertanya gitu ya.
Electric field lines are originate from positive charge and terminate to negative charge. But if there is no negative charge, in this case the electric field lines are originate from positive charge and terminate to infinity. While in case of magnetostatics, the steady magnetic field is produced by permanent magnet having north pole and south pole, and surrounding this permanent magnet there is a steady magnetic field, and the direction is from north pole to south pole outside the magnet and south pole to north pole inside the permanent magnet. Also, if we consider a conductor through which a DC current is flowing, and surrounding this conductor there is a steady magnetic field. The direction of the steady magnetic field is determined by using right hand thumb rule. Here the thumb is the direction of the current and the curl of the finger is the direction of the magnetic field. So the left side of this conductor, the direction is outward, that is denoted by dot, and right side it is in. And this closed path is a circle and having a constant radius. Here we note a point. In case of electrostatic, isolated electric charge exists. But in case of magnetostatic, the isolated magnetic charge, that is Q suffix m, does not exist. Because if we are interested to separate the north pole and south pole, we get two new magnets. So this is a difference between electric charge and magnetic charge. Now, in electrostatic, we consider charge distribution, and in magnetostatic, we consider current distribution. So, in electrostatic, the current distribution are of three types. First is line charge, second is surface charge, and third is volume charge. In case of line charge, we consider a line on which a uniform charge distribution exists, and here we consider a line charge density rho L. Rho L is the ratio of dq upon dl. On this line, there is a constant charge distribution, and here we consider a small differential length dl. On this small differential length, we consider a small charge dq. So if we take a ratio dq upon dl, it becomes a line charge density and unit is coulomb per meter. And to determine the total charge on this line, we take a line integration of rho L into dl. Here the line integration is single integration. Next is surface charge distribution. Here we consider a surface on which there is a uniform charge distribution. And here we consider a differential surface ds. On this differential surface ds, we consider small charge dq. So after taking a ratio, that is dq upon ds, it becomes a surface charge density rho s, and its unit is coulomb per meter square. So dq is the small charge on small surface ds. To determine the total charge, we take a surface integration of rho s into ds. Here the surface integration is double integration. And the third is volume charge distribution. Here we consider a volume, that is a solid one. In this volume, there is a constant charge distribution. For this, we consider a differential volume dV. On this differential volume, there is a small charge dq. So the ratio dq upon dV is called the volume charge density rho v, and its unit is coulomb per meter cube. And for the total charge on this volume, we consider a volume integration of rho v into dV. Here volume integration is triple integration. And in case of magnetostatic, we consider a current distribution. So there are three types of current element in magnetostatic. First is line current element, second is surface current element, and third is volume current element. In line current, we consider line in which a current I is flowing, and here we consider a small differential length dl. On this differential length dl, there is a constant current I, so here the line current is I into dl vector. I into dl vector is a line current element and its unit is ampere meter. Second is surface current element. In this we consider a surface. On this surface a uniform current is flowing. In this case we consider a surface current density that is denoted by K, and its value is current upon perpendicular distance B. Here B is the perpendicular distance and the unit of K is ampere per meter. So in this case the surface current element is denoted by K vector into ds, and its unit is also ampere meter because the surface current density is ampere per meter and the differential surface is meter square, so its unit is ampere meter. Here we note a point. If the surface is in the form of cylinder, in this case we consider a parameter of a circle. So here the surface current density K is equals to I upon 2 pi rho. Here 2 pi rho is the parameter of a circle, that is a perpendicular distance, and its unit is ampere per meter. Third is volume current element. In this we consider a volume through which a constant current is flowing, and here we consider a volume current density denoted by J, and it is a ratio of current upon area, that is cross sectional area, and the volume current element is J vector into dV. Here also the unit of volume current element, that is J vector into dV, is ampere meter because the J, that is volume current density, is ampere per meter square, and here the differential volume dV is meter cube, so unit is ampere meter. So in case of current distribution, that is line current, surface current, volume current, all having a unit that is ampere meter. So this is a difference between charge distribution and current distribution. Next is in electrostatic, the electric fields are E vector and D vector. Here E vector is electric field intensity and D vector is electric flux density. Similarly in magnetostatic, the magnetic fields are H vector and B vector. Here H vector is magnetic field intensity and B vector is magnetic flux density. So in electrostatic, to determine the electric field intensity E, we use a Coulomb's law. And in magnetostatic, to determine the magnetic field intensity H vector, we use a Biot-Savart's law. These are called a general law. So here we consider first Coulomb's law. In a Coulomb's law, we consider a static charge which produces a static electric field. In this static electric field, we consider a test charge denoted by Q suffix T. Since both are positive charge, so it repel with each other, and here we consider a charge Q as a static. This is fixed, and here the test charges move with some force, that is F suffix T, and there is a distance between two charges that is noted by capital R and the form of vector, it having a unit vector, that is unit vector R. And according to Coulomb's law, the force is directly proportional to product of the charge, that is Q into Q suffix T, and the inversely proportional to square of the distance between them. And here there is a constant of proportionality K, and its value is 1 upon 4 pi epsilon naught. So the force on test charge is denoted by F suffix T, and it is a repulsive. It is equals to Q into Q suffix T upon 4 pi epsilon naught R square unit vector R. This is called a Coulomb's law. And with the help of this, we can determine the electric field intensity E vector, and it is a ratio of force per unit test charge. And its unit is Newton per Coulomb. Another is volt per meter. So the electric field intensity E equals to Q upon 4 pi epsilon naught R square unit vector R. And in place of unit vector R, we can write vector upon its magnitude. So the formula is Q into R vector upon 4 pi epsilon naught R cube. And since in electrostatic there are three charge distribution, line charge, surface charge and volume charge. So for determining the electric field intensity in place of Q, we can write line integration rho L dl in case of line charge and surface integration of rho s ds in case of surface charge, and volume integration rho v into dv in case of volume.
Baut zuerst Straßen und Brücken. Die Kaserne.
Charge distribution. And in magnetostatic, the general law is Biot-Savart's law. It is used to determine the magnetic field intensity H vector. Here we consider a line in which there is a constant current flowing, that is I, capital I. And to determine the magnetic field intensity H vector surrounding this current carrying conductor, we use a Biot-Savart's law. For this, we consider a current element, that is I into dl vector, and due to this current element, we first determine the dH, that is a small differential magnetic field intensity at any point. Here we consider a point to the right side, so the direction is in, that is determined with the help of right hand thumb rule, and this point is at a distance of r with respect to current element I into dl vector. Here the current element I into dl vector makes an angle alpha with respect to r. So according to Biot-Savart's law, the small differential magnetic field intensity, that is dH, is directly proportional to product of I into dl and sine alpha, and inversely proportional to square of the distance between them. Here the constant proportionality is 1 upon 4 pi. So in magnitude form, the dH is equals to I into dl sine alpha upon 4 pi r square, and in terms of vector, it is dH vector, and here we consider a cross product, that is cross product of I into dl vector and unit vector r. So the small differential magnetic field intensity dH vector equals to I into dl vector cross unit vector r upon 4 pi r square, and its unit is ampere per meter. Now to determine the total magnetic field intensity, we take a line integration in case of line current element, which is I into dl vector, and in case of surface current element, we consider a surface integration, that is double integration, and here the surface current element is k vector into ds, and in case of volume current element, we take a volume integration, and here the volume current element is j vector into dv, and in place of unit vector r, we can write vector upon its magnitude. Now next difference is on the basis of flux density. In electrostatic, we consider a electric flux density denoted by capital D vector, and its unit is coulomb per meter square. In magnetostatic, we consider a magnetic flux density denoted by capital B vector, and its unit is Weber per meter square. Another unit of magnetic flux density B vector is Tesla. Now in free space, the electric flux density D vector is epsilon naught E vector. Here epsilon naught is called a permittivity in free space, and its value is 8.854 into 10 to the power minus 12 farad per meter. Approximately it can be written as 10 to the power minus 9 upon 36 pi farad per meter. And in magnetic flux density B vector, it is written as mu naught into H vector. Here mu naught is permeability in free space, and its value is 4 pi into 10 to the power minus 7 Henry per meter. In electric flux density, we consider a electric flux, that is a surface integration of D vector into ds vector, and its unit is coulomb. And in case of magnetic flux density, we consider a magnetic flux, and it is equals to surface integration B vector dot ds vector, and here the unit is Weber. Now we represent a electric flux lines. Electric flux lines crosses the differential surface ds, and that is denoted by capital D vector, that is called electric flux density. So after taking a dot product of D vector and ds vector, we get a electric flux. The electric flux lines may be open or closed, so there exists a divergence of capital D vector. But in case of magnetic flux lines, these are always closed one, so there is no existence of divergence of D vector. So this is difference. In electric flux lines, it may be open or closed, so divergence exists, but in magnetic flux lines, it is always closed, so there is no divergence of B vector, that is magnetic flux density. Now we consider electric flux density for all the three charge distribution, that is line charge, surface charge and volume charge. In case of line charge, D vector is line integration rho L dl upon 4 pi r square unit vector r. In surface charge distribution, D vector is surface integration rho s ds upon 4 pi r square unit vector r. And volume charge distribution, D vector is volume integration rho v dv upon 4 pi r square unit vector r. In place of unit vector r, we can write vector upon its magnitude. Similarly, in magnetostatic, we consider a current distribution. So there are three current distribution. First is line current, second is surface current, and third is volume current. So in case of line current, the magnetic flux density B vector is line integration mu naught I dl vector cross unit vector r upon 4 pi r square, because we know that B vector equals to mu naught h. And in place of unit vector r, we can write vector upon its magnitude. In case of surface current, B vector equals to surface integration mu naught k vector ds cross unit vector r upon 4 pi r square. In place of unit vector r, we can write vector upon its magnitude. In case of volume current, B vector is volume integration mu naught j vector dv cross unit vector r upon 4 pi r square. Here also, in place of unit vector r, we can write vector upon its magnitude. Next difference is based upon a continuous distribution. In case of electrostatic, there is a continuous charge distribution, that is Q, and in case of magnetostatic, there is a continuous current distribution, that is capital I. So for this, in electrostatic, Gauss's law is used, and in case of magnetostatic, Ampere's circuit law is used. So first we talk about Gauss's law for electrostatic. According to Gauss's law, closed surface integration d vector dot ds vector is equals to charge enclosed, which means that if we consider any point charge q, surrounding this point charge we consider a closed surface. This is an assumed surface, that is called a Gaussian surface, and due to a positive charge, the electric flux density d vector is radially outward. So
jadi ini tadi dijelaskan dari awal bagaimana kita mempelajari mengenai persamaan dan perbedaan antara elektrostatik dan magnetostatik. Ya, di dalam elektrostatik ini kemarin kita sudah bahas ya mengenai yaitu Gaussian, ya, bahwa integral tertutup ya ini dalam satu luasan tertentu gitu ya, Gaussian. Ya, dari sini sama dengan divergensi ds atau gradien d dv rho dv ini yang tertutup di sini ya. Sedangkan di sini Ampere's law itu yaitu pada lintasan tertutup ya arus yang enclosed, yang di dalamnya itu integral, ini lintasan, di sini luasan gitu ya. Kemudian kita kembali lagi ke sini ke ke awal tadi ya, perhatikan bahwa arus yang kalau seperti ini itu maksudnya itu adalah ke dalam kita ya, ke sini. Jadi kaidah tangan jempolnya itu. Saya mundur lagi sedikit lagi. Tunjukkan ini ya. Jadi kalau arusnya ke sana, maka yang sebelah sini masuk begitu ya. Jadi kalau kita perhatikan itu kaidah tangan kanannya itu seperti itu. Ya, kalau Anda perhatikan, ya, jadi ini arusnya ke sana, maka yang sebelah sini dia akan masuk begitu ya. Jadi perhatikan jempolnya begitu, terus kaidah tangan kanan. Jadi intinya itu seperti ini ya. Ini kalau ini arusnya ke sana, maka sebelah sini masuk kemari. Jadi jempolnya ini sebagai arah arus. Jempolnya sebagai arah arus. Oke, kita kembalikan. Kalau nggak jelas, silakan bertanya ya. Langsung aja tanya saja. Ini penjelasannya ini menarik ini yang apa namanya saudara kita dari India ini. Saya kemarin mencari videonya sangat bagus sekali dan detail menjelaskannya, komprehensif. Oke, silakan.
According to Desember's law, the small differential magnetic field intensity, that is dH, is directly proportional to product of I into dl and sine alpha, and inversely proportional to square of the distance between them. Here the constant proportionality is 1 upon 4 pi. So in magnitude form, the dH is equals to I into dl sine alpha upon 4 pi r square. And in terms of vector, it is dH vector, and here we consider a cross product. That is cross product of I into dl vector and unit vector r. So the small differential magnetic field intensity dH vector equals to I into dl vector cross unit vector r upon 4 pi r square, and its unit is ampere per meter. Now to determine the total magnetic field intensity, we take a line integration in case of line current element, which is I into dl vector, and in case of surface current element, we consider a surface integration, that is double integration, and here the surface current element is k vector into ds, and in case of volume current element, we take a volume integration, and here the volume current element is j vector into dv, and in place of unit vector r, we can write vector upon its magnitude. Now next difference is on the basis of flux density. In electrostatic, we consider a electric flux density denoted by capital D vector, and its unit is coulomb per meter square. In magnetostatic, we consider a magnetic flux density denoted by capital B vector, and its unit is Weber per meter square. Another unit of magnetic flux density B vector is Tesla.
Ini kalau electric flux density ini ya kita biasanya pergeseran ya displacementnya. Kita perhatikan di sini untuk di bahan dielektrik ini adalah permitivitas, di magnetik itu permeabilitas, gitu ya.
Now in free space, the electric flux density D vector is epsilon naught E vector. Here epsilon naught is called a permittivity in free space, and its value is 8.854 into 10 to the power minus 12 farad per meter. Approximately, it can be written as 10 to the power minus 9 upon 36 pi farad per meter. And in magnetic flux density B vector, it is written as mu naught into H vector. Here mu naught is permeability in free space, and its value is 4 pi into 10 to the power minus 7 Henry per meter. In electric flux density, we consider a electric flux, that is a surface integration of D vector into ds vector, and its unit is coulomb. And in case of magnetic flux density, we consider a magnetic flux, and it is equals to surface integration B vector dot ds vector. And here the unit is Weber. Now we represent a electric flux lines. Electric flux lines crosses the differential surface ds, and that is denoted by capital D vector, that is called electric flux density. So after taking a dot product of D vector and ds vector, we get a electric flux. The electric flux lines may be open or closed, so there exists a divergence of capital D vector. But in case of magnetic flux lines, these are always closed one, so there is no existence of divergence of B vector. So this is a difference. In electric flux lines, it may be open or closed, so divergence exists, but in magnetic flux lines, it is always closed, so there is no divergence of B vector, that is magnetic flux density. Now we consider electric flux density for all the three charge distribution, that is line charge, surface charge, and volume charge. In case of line charge, D vector is line integration rho L dl upon 4 pi r square unit vector r. In surface charge distribution, D vector is surface integration rho s ds upon 4 pi r square unit vector r, and volume charge distribution, D vector is volume integration rho v dv upon 4 pi r square unit vector r. In place of unit vector r, we can write vector upon its magnitude. Similarly, in magnetostatic, we consider a current distribution. So there are three current distribution. First is line current, second is surface current, and third is volume current. So in case of line current, the magnetic flux density B vector is line integration mu naught ideal vector cross unit vector R upon 4 pi R square, because we know that B vector equals to mu naught H. And in place of unit vector R, we can write vector upon its magnitude. In case of surface current, B vector equals to surface integration mu naught K vector ds cross unit vector R upon 4 pi R square. In place of unit vector R, we can write vector upon its magnitude. In case of volume current, B vector is volume integration mu naught J vector dV cross unit vector R upon 4 pi R square. Here also, in place of unit vector R, we can write vector upon its magnitude. Next difference is based upon a continuous distribution. In case of electrostatic, there is a continuous charge distribution, that is Q, and in case of magnetostatic, there is a continuous current distribution, that is capital I. So for this, in electrostatic, Gauss's law is used, and in case of magnetostatic, Ampere's circuit law is used. So first we talk about Gauss's law for electrostatic. According to Gauss's law, closed surface integration d vector dot ds vector is equals to charge enclosed, which means that if we consider any point charge q, surrounding this point charge we consider a closed surface. This is an assumed surface, that is called a Gaussian surface, and due to a positive charge, the electric flux density d vector is radially outward. So on this Gaussian surface we consider a differential surface ds vector, and the direction of this ds vector is also normal. So the direction of ds vector and d vector is same. And after taking a dot product over a closed surface integration, that is equals to a charge enclosed by this Gaussian surface, and this is called a Gauss's law. And we know that the charge q can be written in terms of volume integration rho v into dv, because here we consider a charge as a spherical, which is a solid one which occupies some volume. And here, in case of Gauss's law, we take a closed surface integration, and we know that any closed surface defines a volume. So this is a relationship of the closed surface integration and volume integration, that is a divergence theorem. So closed surface integration d vector dot ds vector is equals to volume integration divergence of d vector into dv. And here on both the sides we get a volume integration, and after comparing we get a divergence of d vector equals to rho v.
Wiegst du dich auch regelmäßig und setzt dich das auch unter Druck und stresst dich? Wusstest du, dass immer bei Stress...
This is called a Maxwell's equation, that is divergence of d vector equals to rho v. Because we know that in case of electrostatic, isolated electric charge exists, so the divergence exists. And the divergence of d vector equals to rho v, that is volume charge density, and this is a Maxwell's equation. Also, in case of point charge, d vector equals to q upon 4 pi r square unit vector r. And in case of infinite line charge, the electric flux density d vector is rho l upon 2 pi rho unit vector rho. Here rho is the radius of a cylinder, that is a line, and rho l is a line charge density. In case of infinite sheet charge, d vector is rho s upon 2 unit vector z. Here rho s is surface charge density. And in case of magnetostatic, there is an Ampere's circuit law that is used for continuous current distribution, and according to Ampere's circuit law, closed line integration h vector dot dl vector is equals to current enclosed. Here we consider a conductor which carries a current I. Due to this constant current, there exists a steady magnetic field surrounding this current carrying conductor. And to determine the magnetic field intensity at any point, we consider a closed path. This closed path is called a Amperian closed path, and this must pass through a point at which we have to determine the magnetic field intensity H. So on this closed path, that is a circle one, which having a constant radius rho, here we consider a cylindrical coordinate system. On this closed path, we consider a differential length dl vector, and on this closed path, the h vector make a tangent. So there is an angle between h vector and dl vector, and after taking a dot product of H vector and dl vector over a closed path, we get a Ampere circuit law. So after taking a closed line integration of H vector dot dl vector, and this is equals to current enclosed by this Amperian closed path. And we know that to determine the current, we use a current density J vector. So I is equals to surface integration J vector dot ds vector. Also, we know that any closed path defines open surface. So this is a relationship of the closed line integration and surface integration that is defined by a Stokes theorem. So according to Stokes theorem, closed line integration H vector dot dl vector is equals to surface integration of curl of H vector dot ds vector. Now we get a surface integration on both sides, and after comparing we get a Maxwell's equation, that is curl of H vector is equals to J vector. So this is a Maxwell's equation in case of Ampere circuit law. Now since there is no existence of isolated magnetic charge, so there is no formula for magnetic charge, that is isolated magnetic charge. Next is for infinite line current, H vector is equals to I upon 2 pi rho unit vector phi. And in case of infinite sheet of current, H vector is equals to 1 upon 2 k vector cross unit vector n. Here unit vector n is the normal unit vector of the infinite sheet. And also k is surface current density, and it is I upon b. B is a perpendicular.
Be honest, do you really want to watch a video that looks like this? There's a good reason why presenters use
distance. Now we note a point. The Gauss's law in charge enclosure. There is also a Gauss's law in magnetostatic, that is closed surface integration B vector dot ds vector, and it is equals to 0, because we know that in magnetostatic there is no existence of the isolated magnetic charge, or there is no separation of North Pole or South Pole. So according to this, we can use a relationship that is a closed surface integration and volume integration, that is by divergence theorem. So here we use a divergence theorem, so it is equals to volume integration of divergence of B vector into dV. And this is also equals to 0, so we can write divergence of B vector equals to 0, and this is another Maxwell's equation. In magnetostatic, the magnetic flux lines are closed one, it is always closed, so there is no divergence of B vector. So divergence of B vector equals to 0, and this is called a law of conservation of magnetic charge. Next difference is on the basis of potential. In electrostatic, we consider a scalar potential that is denoted by capital V, and in case of magnetostatic, we consider scalar potential as well as vector potential. So in case of electrostatic, there is only scalar potential that is scalar electric potential, and in magnetostatic there is scalar magnetic potential denoted by V suffix m, and scalar vector potential denoted by capital A vector. So first we discuss the scalar electric potential, that is capital V. For this we consider an electric field, and in this electric field we consider a charge Q, and we move this charge Q against the electric field by some differential distance dl vector. So here we displace a charge Q with some differential length from A to B. So there is a change in potential, and that is denoted by V suffix AB. That is potential difference between point A and B. And this is a ratio of work done per unit charge, which means that when we displace a charge Q against the electric field, so we have to done some work against the electric field. So it is equals to minus integration E vector dot dl vector. Here the limit is from A to B. And here we consider a negative sign because here we displace Q against the electric field. And the potential difference between 2 points is equals to V suffix B minus V suffix A, where VB and VA are called the absolute potential at point A and B with respect to origin. And here we note a point. The potential difference is a path independent, means it does not depend upon the path between A and B. So here we consider XYZ axis, and in this plane we consider 2 points A and B. At point A the absolute potential is VA, and at point B the absolute potential is V suffix B. And these potentials makes a position vector RA and RB with respect to origin. So absolute potential is always with respect to 0, and to determine the potential difference, that is between point A and B, and it is equals to VB minus VA, because here we displace from point A to B, so the formula is VB minus VA. It is also equals to Q upon 4 pi epsilon naught within bracket 1 upon RB minus 1 upon RA. So this is the potential difference in terms of charge Q. And also the absolute potential at any point is equals to Q upon 4 pi epsilon naught R. This is a general formula to determine the electric potential. Now we note an important point. To determine the potential at any point A, we consider a charge Q, that is a test charge, and we move that test charge from infinity to the point at which we have to determine the potential. And we know that at infinity the potential is 0. So according to our formula, the potential difference between infinity and point A is equals to Q upon 4 pi epsilon naught within bracket 1 upon RA minus 1 upon infinity, because here we consider a absolute potential with respect to origin. So at point A the position vector is RA, and for infinity the distance is infinite. So after putting the values, we get a potential difference between point A and infinity, and it is equals to Q upon 4 pi epsilon naught RA, because we know that 1 upon infinity is equals to 0, and this potential difference is equals to V infinity minus VA, and potential at infinity is 0, so it is equals to VA. So we can determine potential at any point A, and it is equals to Q upon 4 pi epsilon naught RA. Here RA is the position vector with respect to origin, and in general we can write V equals to Q upon 4 pi epsilon naught R. And in terms of electric field intensity, it is equals to minus integration E vector dot dl vector, and the limit is from infinity to any position R. So this is about electric scalar potential. Now we discuss the relationship between electric field intensity E vector and electric potential V. For this we consider an electric field. In this electric field we consider a 2 point A and B, and when we displace any test charge from A to B or B to A around a closed path, we get a closed line integration E vector dot dl vector, and its value is always 0. Now we consider Stokes theorem, that is the relationship of the closed line integration and surface integration. So closed line integration E dot dl vector is equals to surface integration curl of E vector dot ds vector, and it is equals to 0. From here we get another Maxwell's equation, that is curl of E vector equals to 0. That is called a Maxwell's curl equation. And we know that the electric scalar potential V can be written as minus integration E vector dot dl vector, and in terms of differential potential, that is dV equals to minus E vector dot dl vector. So in place of E vector we can write minus dV upon dl, and dV upon dl is gradient of potential, that is del V. So this is a relationship, that is E vector is equals to minus gradient of electric potential. Also in terms of charge distribution, the potential for line charge is line integration rho L dl upon 4 pi epsilon naught R. In case of surface charge, the potential is surface integration rho S ds upon 4 pi epsilon naught R. And in case of volume charge, the potential is volume integration rho V dV upon 4 pi epsilon naught R. So in case of electric scalar potential, we consider Laplace equation and Poisson's equation. That is obtained from Laplacian of a scalar and Laplacian of a vector. So Laplace equation is del square V equals to 0 and Poisson's equation is del square V equals to minus rho V upon epsilon naught. Now we talk about potential in magnetostatic. There are two types, magnetic scalar potential denoted by V suffix m and magnetic vector potential denoted by A vector. First we talk about magnetic scalar potential, that is V suffix m. We know that in electrostatic the relationship is E vector equals to minus gradient of V. So we use this relationship for magnetic scalar potential, that is H vector equals to minus gradient of V suffix m. And this relationship exists only when we consider a current density J vector equals to 0. So we can say that the magnetic scalar potential exists in a region where current density is 0. And we know that Ampere's circuit law is curl of H vector equals to J vector. And in place of H vector, we can write minus gradient of V suffix m. And here we consider a vector identity, that is a curl of gradient of a scalar is always equals to 0. So here the curl of minus gradient of V suffix m is also equals to 0 by using vector identity, and from here we get a Laplace equation, that is del square V suffix m equals to 0. So we can say that in case of magnetic scalar potential, Laplace equation is satisfied. Next is called a magnetic vector potential denoted by capital A vector. So the magnetic vector potential A vector is defined such that when we take a curl of A vector, it gives a magnetic flux density B vector. So to define magnetic vector potential, we take a curl of A vector equals to B vector. And in case of magnetic vector potential, Poisson's equation is satisfied. So the Poisson's equation in magnetostatic is del square A vector equals to minus mu naught J vector. That is similar to the Poisson's equation of a electrostatic. Now to determine the magnetic vector potential for line current, surface current and volume current, we compare it with the electric potential. So in electric potential, V is directly proportional to rho L dl or rho S ds or rho V dv. Similarly, A vector is directly proportional to I dl vector or K vector into ds or J vector into dv. Electric potential V is inversely proportional to 4 pi small r and A vector is inversely proportional to 4 pi capital R. And electric potential is inversely proportional to epsilon naught, but in case of magnetic vector potential, A vector is directly proportional to mu naught. So the magnetic vector potential is related to electric scalar potential. Only the difference is that in case of electric potential, epsilon naught is in denominator, and in case of magnetic vector potential, mu naught is in numerator. Next comparison is, in electrostatic we talk about polarization in dielectric material, that is denoted by capital P vector. And in magnetostatic we talk about magnetization in magnetic material, that is denoted by capital M vector. So first is polarization. Polarization in dielectrics. Polarization is denoted by capital P vector and it is equals to summation of dipole moment per unit volume as volume tends to 0. And the unit of polarization is coulomb per meter square, because we know that the dipole moment is Q into D vector and its unit is coulomb meter.
Ini nanti kita pelajari di Medan Elektromagnetika 2 ya, ketika kita bahas mengenai bagaimana di material begitu. Tapi saya kembalikan ke sini lagi ya, terkait dengan yang pertama.
But in case of magnetic vector potential, A vector is directly proportional to mu naught.
Kalau yang
the magnetic vector potential,
kalau potensial listrik itu ya permitivitas ya, sedangkan di magnet itu permeabilitas Ya, nantinya kita akan secara detail mu0, kebetulan kita di Medan Elektronika 1 ini kita bahas masih di hampa ya. Tadi kita belum kita bahas belum ke ke material begitu ya. Jadi ini pelajaran yang kita pelajari ya. Jadi sejauh ini kita belajar untuk yang adalah medan magnet, medan listrik itu dengan Gauss law ya. Kemudian kalau di dalam magnetostatik itu ada ampere ya. Kalau di dalam medan itu listrik itu integral tertutup ya, D.dA sama dengan muatan rho dV atau muatan terlimbuki ya dibagi dengan epsilon 0. Sedangkan di dalam magnetostatik ada hukum ampere yaitu integral tertutup B.dl sama dengan I enclosed, arus yang terlingkupi. Ya, satunya integral lintasan, satunya luasan. Begitu. Ya. Di sisi medan listrik itu adalah permitivitas, di sisi medan magnet itu adalah permeabilitas. Tentu nanti permeabilitas dan permitivitas ini nanti kita pakai di dalam pembahasan berikutnya. Ya, termasuk ini adalah basic semuanya. Kalau misalkan kita ingin berbicara terkait dengan aplikasi di dalam kehidupan kita banyak sekali ya untuk karakterisasi bahan di elektrik gitu, keramik seperti Prof. Suasmoro itu menganalisa permitivitasnya ya, kemudian mencari bahan-bahan keramik yang tahan pada temperatur tertentu, yang memiliki resonansi pada frekuensi tertentu ya. Sedangkan untuk di dalam dunia medis nanti kita akan bahas mengenai dipol ya, momen-momen dipol magnetik maupun dipol listrik ya. Kalau di dalam aplikasinya itu kita menggunakan MRI ya, pakai pada waktu terapi ya. Jadi radioterapi itu MRI pakai magnetik di luar, kemudian di dalam tubuh manusia, sehingga dengan MRI ini kita bisa melihat citra di dalam tubuh, di mana di dalam tubuh manusia itu terdapat dipol, baik dipol listrik maupun dipol magnetik. Yaitu kira-kira pertemuan kita kali ini. Ya, silakan kalau ada pertanyaan atau komentar. Ya tadi saya mendapatkan dapat video ini sangat bagus sekali. Ada seorang kolega dari India itu yang membandingkan ya antara medan listrik sama medan magnet. Gitu. Kalau tidak ada saya akhiri ya.
Tanya Pak Prof.
Silakan Mas Rizky.
Ya, mau tanya itu kok tulisan dari kolega India tadi. Kok
videonya?
Lambda vektornya. Iya, lambda vektornya itu yang benar bentuk kail apa kayak gitu, Pak?
Oh, vektornya itu.
Iya kok.
Harusnya sama kail itu, arah itu enggak yang benar kail. Ya. Baik, Pak. Mungkin karena dia mempermudah saja panah, tapi sebenarnya enggak. Vektor yang benar itu kail gini. Seret gitu ya. Bukan panah. Memang seringkali saya ada beberapa yang tidak memperhatikan tetapi simbol yang benar itu kail, Mas Rifki. Seperti ini seret gitu.
Iya, Pak. Makasih banyak,
Pak. Bukan panah.
Pak, saya mau tanya, Pak.
Oke, Mas Nabian.
Tadi kan buat medan magnet itu ada yang dilambangkan B, ada yang dilambangkan H. Itu apa ada perbedaannya, Pak, antara yang B dan yang H?
Ada. Kalau H itu B itu kan sama dengan mu kali H. Nanti kita pelajari di medan elektromagnetik 2 nantinya. Yang satunya kan ya ada macam-macam. Yang satu H itu dikatakan intensitas, yang B dikatakan flux magnetik. Kalau tadi itu ada beragam. Tetapi H dan B beda, Mas. Ya hubungannya. Kalau E D itu kan sama dengan permitivitas di epsilon 0 dikalikan dengan E gitu ya. Nah, maka B itu sama dengan U kali H. Beda, H sama B itu suatu besaran fisis yang berbeda.
Itu bedanya di mana ya Pak? Di sumber medan magnetnya atau emang itu medan yang berbeda Pak?
Belum enggak, apa namanya itu, ya sumbernya sama. Dari ada arus ya, kemudian arus mengalir gitu kan. Nah, di situ di satu titik itu kita bisa menghitung H dan B-nya di situ.
Oh,
Pada jarak tertentu itu ada bisa kita mengatakan hanya sama medan listrik. Kalau saya ada muatan gitu ya, maka kalau dia lewat kalau nanti kelihatan di material Mas. Untuk sementara ini kita masih berdiskusi mengenai sebentar saya carikan dulu ya di dalam Griffith, bukunya Griffith ini. Ya, supaya nanti ada bedanya antara B dan H itu ya. Ada H itu B sama dengan mu dikalikan dengan H. Gitu. Ini hukum Gauss, bentar. Ini tadi hukum ampere ya, B dl mu includes. Ya, sebentar saya carikan. B itu sama dengan mu kalikan H. Sini tidak ada. Nanti Mas di bab lebih jelas nanti kita di Medan Elektromagnetika 2. Nah, ini coba ini materi ketidaknambahan. Nah, nanti di sini ada. Nah, ini Mas. Ya. B sama dengan mu dikalikan dengan H. Ya, jadi ini biasanya kita bicara mengenai intensitas magnetik, di sini adalah magnetiknya. Atau kadang orang menyebut ini flux magnetik begitu. Ya, jadi B itu sama dengan mu dikalikan H. Nah, tetapi bagaimana kalau misalkan di sini ada arus, misalkan di sini ada arus begitu ya, ada arus mengalir. Bentar. Keluar ininya. Ya, gitu ya. Ini jadi B sama dengan mu kali H. Coba kalau saya saya tunjukkan tadi di dalam video tadi ya. Nah, di dalam biosafat ini ya, misalkan di sebelah sini, ini kita bisa ini arus mengalir ke sana ya, arus mengalir ke sana. Maka kita bisa mencari di sini, kita bisa mencari hanya, maka kita juga bisa mencari B-nya di sini. Ya, besarnya B di sini sama dengan mu 0 dikalikan H, gitu Mas. Ya, jadi besaran B itu adalah tadi bisa dikatakan sebagai medan magnet ya, bisa orang mengatakan flux magnetik begitu. Mana nilai B itu sama dengan mu kalikan A. Kalau seandainya apa namanya itu arus mengalir begini, kemudian di sini ada material, ya maka B di sini sama dengan mu permitivitas bahan itu dikalikan dengan hanya, gitu. Itu Mas Nabian.
Oh, jadi besarannya emang beda ya, Pak?
Beda. Besarannya beda.
Oh iya, makasih Pak.
Oke. Silakan kalau ada yang mau bertanya atau memberikan komentar ya.
Pak izin bertanya.
Iya, Mbak Titi.
Izin bertanya Pak.
Ya.
Tapi ini cuma tanya simbol aja sebenarnya.
Iya.
Itu yang A vektor sama itu apa nggih?
Oh potensial
yang
vektor.
A terus panjang atas.
Potensial vektor magnetik.
Yang itu yang J.
Yang J itu rapat arus persatuan luas J.
Oh, iya.
J itu rapat arus persatuan luas satuannya itu ampere per meter persegi. Ini tadi sebentar saya tunjukkan lagi ya tadi. Nah, ini kan tadi ada A kan potensial. Bentar. Terus di sini dikatakan nah ini kan ada besaran skala di sini potensial, di sini potensial ya, vektor vektor ini ya magnetik A itu Mas. Nanti untuk sama lebih detail dibaca di bukunya Griffith ya atau di bukunya Prof Mahmud Zaki. Kalau misalkan bahasa Inggris kurang bisa pakai bahasa Indonesia. Satu lagi yang ingin saya info bahwa di medan listrik ini permitivitas, di sini permeabilitas. Jadi J ini adalah rapat arus persatuan luas. Ya, nanti rapat arus persatuan luas nanti akan menentukan hukum ampere ini. HDL sama dengan E inclus ya. Di mana E ini adalah J.dA. D ini rapat arus persatuan luas ya, di S-nya itu luasan yang di sana. Jadi nanti mutar seperti ini. Oke, silakan ada pertanyaan lagi. Terima kasih Mbak Titis. Oke, kalau tidak ada saya akhiri ya sampai di sini ya. Nanti kita hari berikutnya Jumat ya. Bukan sih. Oh Jumat ya, Jumat pagi ya.
Ya Pak, Jumat jam 9 Pak.
Jumat jam 9 ya. Iya. Kadang-kadang aktivitasnya banyak, kadang lupa saya jam 9 nggih. Saya kira gitu nggih. Baik, saya kiri aja pertemuan kita kali ini. Ya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam wabarakatuh.
Waalaikumsalam.
Terima kasih Pak.
Terima kasih Pak.
Sudah absen semua ya?
Sudah tadi Pak.
Ya.
Oke.